You're about to see something that travelled for millions of years just to pass through our solar system once, and then disappear forever. Right now, 400 million miles from where you're sitting, an object the size of a small mountain is screaming through space at 87,000 miles per hour. It came from another star, and NASA's most powerful telescopes have been locked onto it for 89 days straight. This is 3I/Atlas, the third interstellar object we've ever confirmed, and the first one we've caught with technology advanced enough to actually see what it's made of. The images that just dropped 3 weeks ago revealed something nobody predicted. This thing has a tail, it's outgassing, and the chemicals spewing off its surface don't match anything we've seen in our solar system. Which means you're looking at matter that formed under an alien sun, in conditions that might not exist anywhere within 50 light-years of Earth. But here's what as scientists work in 16-hour shifts. 3I/Atlas is accelerating slightly, unexpectedly, and nobody can agree on why. Before we dive into what these images actually show, if you want to follow this story as it develops, because new data is coming in weekly, subscribe and hit the bell. And if this is exactly the kind of content you're here for, let me know with a like. It genuinely helps more people discover these stories. August 13th, 2024, 2:47 a.m. Mountain Time. The Atlas telescope system in Hawaii picks up something moving against the background stars. At first, it looks like just another asteroid. Faint, distant, unremarkable. But there's something off about its motion. The computer flags it automatically, and within 6 hours, 3 other observatories confirm what the algorithm suspected. This object is moving too fast. Way too fast. You need to understand what too fast means in this context. Every asteroid, every comet, every piece of rock in our solar system is bound by the sun's gravity. They're trapped here, orbiting in predictable patterns that follow rules Newton figured out 300 years ago. Their velocities have an upper limit. But this thing, it's moving at 33 kilometers per second relative to the sun. That's 73,000 miles per hour. And it's not slowing down. It's not curving into an elliptical orbit. It's moving in a hyperbola, which is the mathematical shape that screams one word escape. Within 48 hours, the Minor Planet Center sends out an alert that makes astronomers around the world literally stop what they're doing. The subject line reads, "Possible interstellar object." Because if the trajectory calculations are correct, this thing didn't originate in our solar system. It came from somewhere else, somewhere out there in the galaxy. And it's just passing through. Now, you might think, okay, we've seen this before. Oumuamua in 2017, 2I/Borisov in 2019. What's the big deal about a third one? Here's what's different. When we found Oumuamua, we had already missed it. By the time we knew it was interstellar, it was on its way out, tumbling away from the sun, and our telescopes were barely powerful enough to see it as more than a point of light. We got basically nothing. A few blurry images, a light curve that suggested it was elongated. And then it was gone, leaving behind more questions than answers. 2I/Borisov was better. We caught it on approach, watched it for months, confirmed it was a comet with a beautiful tail, but it stayed relatively far from Earth, about 190 million miles at its closest. We got decent data, sure, but it was still limited. We were looking at it from a distance, trying to piece together its story from faint spectroscopic signatures and low-resolution images. But 3I/Atlas, we caught it early, we caught it close, and most importantly, we caught it during an era when we have the James Webb Space Telescope, the most powerful infrared observatory ever built, already operational and ready to point at whatever we tell it to. Think about that for a second. The first interstellar visitor we ever confirmed. We barely saw. The second one. we studied from afar. The third one, we can actually examine it in detail. The confirmation process took 11 days. That might sound slow, but in astronomy, that's lightning fast. You can't just look at one observation and declare something interstellar. Too much is at stake. The orbit has to be calculated from multiple observations, taken from different locations, over several days. You need to account for Earth's motion, the observer's position, atmospheric distortion, instrumental errors. Every calculation has to be checked, rechecked, and verified by independent teams. Dr. Robert Werrick, the same astronomer who discovered Oumuamua, was one of the first to run the numbers on 3I/Atlas. In an interview with Sky and Telescope published September 1st, he said the eccentricity was immediately suspicious. We were seeing values above 1.5, which is significantly hyperbolic. But you always assume error first. You assume you made a mistake. It took 4 days of additional observations before I was willing to believe what the data was telling us. Eccentricity above 1.5. Let me put that in perspective for you. Earth's orbit has an eccentricity of 0. 017, almost a perfect circle, Halley's Comet, which loops way out beyond Neptune before swinging back, has an eccentricity of 0.967, very stretched, but still bound to the Sun. An eccentricity of exactly 1.0 is the boundary. That's a parabolic orbit, the minimum energy needed to escape the Sun's gravity forever. Anything above 1.0 is hyperbolic, meaning the object has excess velocity. It's not just escaping, it's blasting through. 3I/Atlas clocked in at 1.53. That's not marginally interstellar. That's decisively undeniably from another star system interstellar. On August 24th, the International Astronomical Union made it official. They assigned it the designation 3I/2024Q3, where the I stands for interstellar, and they gave it the name Atlas, after the survey that found it. But here's what nobody expected. When they started pointing serious optical and infrared telescopes at it to characterize what kind of object it was, they saw something that didn't fit either of the previous visitors' profiles. It wasn't dark and rocky like Oumuamua, but it also wasn't exactly like 2I/Borisov's obvious comet behavior. It was something in between, and that in-between status is what made NASA's Planetary Defense Coordination Office make a decision that almost never happens. They issued a director's discretionary time request to Hubble, Webb, and the Keck Observatory simultaneously. That's the astronomical equivalent of pulling the fire alarm. It means drop everything. We need these telescopes now, and we need them working together. Because there was a countdown clock, nobody could stop. 3I/Atlas was going to reach its closest point to the Sun, its Perihelion, on December 3rd, 2024. After that, it would start accelerating outward, driven by the Sun's gravity slingshot, and every day it would get fainter, harder to see, until eventually it would fade beyond the reach of even our most powerful instruments. We had one shot at this, one window, and it was already closing. So what did those first emergency observations reveal that made this object so compelling, so different from anything we'd seen before? The answer came in 3 waves, and each wave made the situation more urgent. Wave 1 hit on August 27th. Hubble Space Telescope completed its first deep exposure of 3I/Atlas, a series of images taken in visible and ultraviolet light over 4.5 hours. When the processed images came back from the Space Telescope Science Institute in Baltimore, the operations team saw something they weren't expecting. The object wasn't a clean point of light. It was fuzzy, surrounded by a faint haze that extended roughly 3,000 miles from the central nucleus. That fuzz has a name in astronomy, a coma. It's a cloud of gas and dust that forms when ice on a comet's surface heats up and sublimates directly from solid to gas, carrying dust particles with it. And here's the thing. Comets from our solar system develop comas when they get close to the sun and warm up. That's normal, that's expected. But 3I/Atlas was still 450 million miles from the sun when Hubble took those images. At that distance, it's barely warmer than the background temperature of space. Our comets don't activate that far out. They stay frozen solid until they cross inside Mars's orbit. So why was this thing already outgassing Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury who was part of the Hubble observation team, told Nature on September 5th, either the object is made of more volatile ices than anything we have in our solar system, or it's been through something that fractured its surface and exposed fresh ice to space. Both possibilities are scientifically exciting and deeply strange. Think about what that means. The composition of comets in our solar system reflects the specific conditions in the disk of gas and dust that formed around our Sun 4.6 billion years ago. The temperature, the pressure, the available elements, all of it created a signature. Our comets are made of water ice, frozen carbon dioxide, a little methane, some ammonia. They're products of this environment, but 3I/Atlas formed somewhere else, around a different star, in a completely different set of conditions. And whatever star system it came from, it created ice that behaves differently than ours. Wave 2 came from the James Webb Space Telescope on September 11th. Webb doesn't take pretty pictures like Hubble. What it does is spectroscopy, breaking down light into its component wavelengths to identify what chemicals are present. And Webb's infrared spectrograph is so sensitive it can detect molecular signatures that are completely invisible to every other telescope we have. The data came back showing strong absorption features at 2.7 microns, 3.3 microns, and 4.26 microns. If you're not an astronomer, those numbers mean nothing to you, but to the scientist analysing the spectra, they meant everything. Those wavelengths correspond to specific molecules carbon monoxide, water ice, and carbon dioxide, respectively. Okay, fine, that's not surprising for a comet, but here's what was surprising. The ratio was wrong. In our solar systems, comets, water ice dominates. It's typically 80 to 90% of the volatile material. Carbon monoxide is a trace component, maybe 1 to 5%, but in 3I/Atlas, the carbon monoxide signature was nearly as strong as the water signature. That's a ratio we've never seen in any object native to our solar system, ever. Dr. Martin Cordner, an astrochemist at NASA's Goddard Space Flight Center, explained it in a NASA press release on September 18th. This is consistent with formation in an extremely cold environment, colder than the outer reaches of our solar system where objects like Pluto formed. We're possibly looking at ice that condensed in a protoplanetary disk around a cooler star, or much farther from a sun-like star than our Kuiper belt extends. You following this? This object is giving us direct physical evidence of conditions in another star system. Not inference, not theory, actual material that formed there and travelled here. Have you ever thought about what that really means? We're analysing alien geology, alien chemistry, the frozen remnants of a world that doesn't orbit our sun. Wave 3 was the kicker. On September 19th, the Keck Observatory in Hawaii, using its adaptive optics system to compensate for atmospheric blurring, captured the highest resolution images of 3I/Atlas taken from Earth. And those images revealed structure in the coma. It wasn't a uniform cloud. There were jets, narrow streams of gas and dust shooting out from specific points on the nucleus, like geysers erupting from the surface. Comets do this all the time. We've seen it on Halley's Comet, on 67P/Churyumov-Gerasimenko when the Rosetta spacecraft visited it. Jets form when sunlight heats specific areas, usually dark patches that absorb more heat, and the ice beneath them vaporizes explosively. But here's what was bizarre about 3I/Atlas. The jets weren't pointing away from the sun. Normally, the most active areas on a comet face the sun because that's where the heating is strongest. But in the Keck images, the brightest jets were oriented almost perpendicular to the sun's direction. That shouldn't happen unless the object is rotating in a specific way, with active vents that happen to be on the sides rather than the sun-facing hemisphere, or unless something else is driving the outgassing beyond just solar heating. The Keck team measured the rotation period from brightness variations roughly 8.7 hours. That's fast, but not abnormally so. But the jet orientation remained unexplained. Dr. David Jewett from UCLA, who studied interstellar objects since Oumuamua, said in a Sky and Telescope interview on September the 24th. We're watching this thing behave in ways that don't fit our models, which means our models are built on a sample size of one solar system. Now we're getting data from outside that sample, and it's showing us we don't know as much as we thought we did. So NASA made a decision. They activated the director's discretionary time not just for a few observations, but for a sustained campaign. From late September through early December, 3A/Atlas would be monitored continuously by a coordinated network of space and ground telescopes. Hubble would track its coma evolution. Webb would take repeated spectra to see if the chemical composition changed as it got closer to the Sun. Keck and other major observatories would monitor its brightness, rotation, and jet activity. This wasn't just about studying one object anymore. This was about seizing a once-in-a-generation opportunity to answer fundamental questions about how planetary systems form, what materials exist in other parts of the galaxy, and whether the building blocks of solar systems are universal or wildly diverse. But to understand what those telescopes were actually looking at, you need to see the images themselves, and you need to know how to read them. Because what shows up in a photograph of an interstellar object isn't always what you think it is. Let me show you what you're actually looking at when you see these images. Because the first time NASA released them to the public on October 3rd, social media exploded with confusion. People were expecting something dramatic, a clear shape, maybe colours. What they got instead were images that, at first glance, looked like smudges on a black canvas. Here's the reality. 3A/Atlas, at its current distance, appears incredibly faint. Its apparent magnitude is roughly 21.3, which means it's about 400,000 times dimmer than the faintest star you can see with your naked eye on a perfectly dark night to even capture it. Hubble had to stare at the same patch of sky for hours, collecting every single photon that bounced off this object and travelled 400 million miles to reach the telescope's sensors. The first image most people saw was a Hubble composite taken over 6 hours on September 29th. It shows a bright central point. That's the nucleus, the solid core of ice and rock, surrounded by a diffuse glow extending outward in an asymmetric pattern. That glow is the coma we talked about. But here's what's not obvious from just looking at it. That central bright point is not actually showing you the shape of the nucleus. The nucleus itself is probably only about 1 to 2 miles across, maybe smaller, at 400 million miles away. That's far too small for even Hubble to resolve. What you're seeing is called a point spread function, basically the blur pattern created by the telescope's optics and the diffraction of light itself. So how do we know anything about the actual shape? We use something called photometry and light curve analysis. As the object rotates, different parts of its surface reflect different amounts of sunlight. If it's spherical, the brightness stays constant. If it's elongated or irregular, the brightness fluctuates. The data from Keck Observatory showed brightness variations of about 0.4 magnitudes over the 8.7-hour rotation period. That translates to roughly a 1.5 to 1 length-to-width ratio, not extremely elongated like Oumuamua, which had ratios estimated at 6 to 1 or even 10 to 1, but definitely not round either. Now look at the second type of image NASA released, the James Webb Infrared observations from October 7th. This one looks completely different. Instead of a visible light photograph, you're looking at a spectrum image, where different wavelengths are spread out vertically. The bright bands you see aren't showing you the object's shape, they're showing you its chemistry. Each bright line corresponds to a specific molecule absorbing or emitting infrared light at a characteristic wavelength. Dr. Stephanie Millam, Webb's deputy project scientist for planetary science, explained it during a NASA press briefing on October 10th. What Webb gives us is essentially a barcode of the object's composition. Every molecule has a unique signature, and we're reading that signature to figure out what this thing is made of. We're not taking a picture, we're taking a chemical fingerprint. And here's where it gets interesting. When the Webb team ran the spectra through their analysis software, comparing it to databases of known molecular signatures, they found something unexpected in the 3.4 micron region. There was a broad absorption feature that's consistent with organic molecules, specifically carbon-hydrogen bonds, the fundamental building blocks of organic chemistry. Before you get excited, organic doesn't mean biological, it just means carbon-based chemistry. But here's why it matters. The presence of complex organic molecules on an interstellar object tells us that the chemistry necessary for life, the raw ingredients, exists in other star systems and can survive the journey through interstellar space. We knew this theoretically, but seeing direct evidence is different. Can you imagine holding a rock that contains molecules formed around another star? Molecules that might be chemically identical to the ones that eventually became you? The third type of image that came out was from the Keck Observatory's Adaptive Optics System, released October 15th. This is where you actually start to see structure. The image shows the coma in much higher resolution than Hubble could achieve from space, because Keck uses a technique that actively corrects for atmospheric distortion in real time. And in that image, you can clearly see the jets we mentioned earlier, narrow streaks extending from the nucleus like spokes on a wheel. The team measured 4 distinct jets, each about 100-200 miles long in the images, though they likely extend much farther before dissipating. By tracking how these jets changed position over multiple nights, they confirmed the rotation period and figured out the orientation of the object's spin axis. It's tilted about 65 degrees relative to its orbital plane, which is actually pretty typical for comets. But what's not typical is that the most active jet, the one producing the most gas and dust, is located near the object's equator, not near a pole where you'd expect maximum solar heating during the rotation cycle. Dr. Jane Liu, who co-discovered the Kuiper Belt and has been observing 3 I/Atlas since late August, published a note in the Astronomer's Telegram on October 18th saying, "The jet activity pattern suggests either compositional heterogeneity across the surface, meaning some areas are richer in volatile ices than others, or we're seeing the effects of recent impacts or fragmentation events that exposed fresh subsurface material. That second possibility is worth thinking about. Interstellar space isn't empty. It contains dust, gas, even the occasional rogue planet. An object travelling for millions of years through the galaxy would absolutely get hit by debris. In fact, cosmic ray exposure dating, a technique where you measure radiation damage in meteorites to figure out how long they've been exposed to space, suggests that many small objects in interstellar space probably get sandblasted and fractured over time. The surface of 3 I/Atlas might be a record of every impact it survived during its journey from wherever it came from to here. And here's the fourth type of image that nobody really talks about, but is absolutely crucial: the astrometric data. These aren't pretty pictures. They're plots showing the object's precise position against background stars over time. measured down to fractions of an arcsecond. These measurements, combined with observations from multiple telescopes around the world, are what let astronomers calculate the trajectory with extreme precision. Because to understand where this thing is going, you first have to understand where it came from, and tracing that path backward through space and time reveals something that still has astronomers arguing in conference rooms and Slack channels about what it means. The math is brutal, but it's also beautiful when you plot 3I/Atlas's trajectory backward through time, accounting for the gravitational influence of every planet it passed, the sun's pull, even the tiny perturbations from Jupiter's moons. You can trace its path through space like rewinding a video. And when a team at the European Space Agency's Near-Earth Object Coordination Centre did exactly that, publishing their results in Astronomy and Astrophysics on October 22nd, they found something remarkable. Go back 3 million years. That's where the trail leads. 3 million years ago, when our ancestors were just beginning to walk upright in Africa, this object was in an entirely different part of the galaxy, moving through a region of space about 470 light-years from where we are now. The team identified the closest approach to a known star system during that time frame, a red dwarf catalogued as WISE-J 085510.83-071442, 5 located in the constellation Hydra. Now, was that its home system? Probably not. The closest it came to that star was still about 1.2 light-years, which is too far for a gravitational ejection to be likely. But here's what matters. The trajectory calculation puts 3I/Atlas in a region of the galaxy dense with young star systems, many of them less than 100 million years old, still surrounded by debris disks where planets are actively forming. This thing likely originated in one of those systems and got kicked out during the chaotic early phase of planet formation. Think about what that process looks like. You've got a young star surrounded by a disk of gas, dust, ice, and rock. Planets start to coalesce from that material, growing bigger through collisions and gravitational accumulation. But it's violent. Absolutely violent. Objects smash into each other at tens of thousands of miles per hour. Protoplanets migrate inward and outward, their gravity scattering smaller bodies in every direction. And some of those smaller bodies, the unlucky ones, get flung out of the system entirely at escape velocity, doomed to wander the galaxy forever. Dr. Piotr Guzik, one of the astronomers who worked on the trajectory analysis, told ESSA in an interview, "We estimate that for every Jupiter-mass planet that forms, hundreds of millions of comet-sized objects get ejected into interstellar space. They're the collateral damage of planet formation, which means the galaxy is full of these things, absolutely full, just drifting between the stars. How full? Let's do the math together. The Milky Way contains somewhere between 100 and 400 billion stars. Most of them probably have planets. If each planetary system ejects even a modest amount of material during formation, say a few Earth masses worth of comets and asteroids, you're looking at trillions upon trillions of interstellar objects out there right now, moving through the darkness. The fact that we've only detected 3 of them isn't because they're rare. It's because they're incredibly hard to see. And here's the thing that keeps astronomers up at night. We're only catching the ones that happen to pass close to the Sun and close to Earth. The vast majority sail through the outer solar system completely undetected. A 2020 study published in the Astrophysical Journal estimated that at any given moment, there's roughly 1 interstellar object somewhere between the Sun and Neptune, just sitting there, invisible, waiting for someone to notice. But back to 3I/Atlas specifically. Once the team established its approximate origin region, they started asking a different question. What can the object's composition tell us about the conditions in that birth system? Because remember, the ice chemistry is weird. That elevated carbon monoxide ratio, the organic molecules, the volatile behaviour at extreme distances from the sun. All of that is data about the environment where it formed. The leading theory, outlined in a paper submitted to Nature Astronomy on October 28th, is that 3I/Atlas condensed in the outer regions of a protoplanetary disk around a star cooler than our Sun, red dwarfs, which make up about 75% of all stars in the galaxy, burn at lower temperatures and emit less ultraviolet radiation than Sun-like stars. In those cooler, gentler environments, certain volatile ices can survive closer to the star, and the chemistry of the disk skews toward carbon-rich compounds rather than oxygen-rich ones. If that's true, and it's still a big if, then 3I/Atlas is giving us our first direct sample of planetary formation around the most common type of star in the universe. Everything we know about planet formation comes from studying our own solar system and observing distant protoplanetary disks through telescopes. But this is holding the actual raw material in our hands, or at least in our telescope sights, and analysing what it's made of. Dr. Daryl Seligman from Cornell University, who specialises in interstellar object dynamics, put it this way in a Twitter thread that went viral on November 2nd. We've been trying to understand how planets form around other stars by looking at fuzzy images of disks millions of light years away. Now, the universe just delivered a piece of one of those disks directly to us. This is like trying to figure out what's in someone's house by looking through their window from across the street, and then they just mail you a brick from their wall. But here's where the story takes a turn. Because while scientists were busy reconstructing 3I/Atlas's past, the object itself was doing something in the present that nobody predicted. Something that showed up in the data as a tiny discrepancy, a mismatch between where the object should be based on gravitational calculations alone and where it actually was in the sky. At first, they thought it was measurement error. Then they thought maybe they'd miscalculated the mass of the object. But as more observations came in through October and into November, the discrepancy didn't go away, it got stronger. And that meant only one thing, something besides gravity, was affecting the trajectory. The anomaly showed up as a deviation of just 15 arcseconds over a 3-week observation period. To put that in perspective, 15 arcseconds is the apparent width of a quarter viewed from 3 miles away. Tiny. Almost negligible. But in orbital mechanics, when you're tracking an object moving at 73,000 miles per hour through the precision gravitational field of the solar system, 15 arcseconds is massive. It's a glaring red flag that something is pushing or pulling on the object beyond what gravity alone can account for. By November 8th, after ruling out observational errors and rechecking the math half a dozen times, the team at NASA's Jet Propulsion Laboratory confirmed it. 3I/Atlas was experiencing non-gravitational acceleration. It was deviating from its predicted path at a rate of approximately 4.6 10⁷ meters per second squared. That number sounds absurdly small, and it is, but integrated over days and weeks, it adds up to a measurable change in trajectory. Now, if you were paying attention during the Oumuamua controversy back in 2017 and 2018, your alarm bells are probably going off right now, because Oumuamua showed the exact same behaviour. It too had a non-gravitational acceleration that couldn't be explained by conventional physics, and that unexplained acceleration is what led to some pretty wild speculation, including the suggestion by Harvard astronomer Avi Loeb that it might be artificial, a light sail or probe from an alien civilization. So is 3I/Atlas an alien spacecraft? Let's talk about what's actually happening here. When a comet heats up, ice on its surface doesn't melt, it sublimates, meaning it goes directly from solid to gas. and when that gas erupts from the surface, it acts like a tiny rocket engine. Every molecule of gas shooting off in one direction pushes the nucleus slightly in the opposite direction. This is called a rocket effect or outgassing thrust, and it's completely normal for comets. We've measured it on dozens of comets in our solar system. It's well understood physics. The problem with Oumuamua was that we never saw any outgassing. No coma, no tail, no detectable gas or dust. It looked like a bare rock, yet it was accelerating as if it were venting material. That mismatch is what made it so controversial. If there's no visible outgassing, what's causing the push? But 3I/Atlas is different. We can see the outgassing, we photographed the coma, mapped the jets, measured the gas production rate. On November 12th, the Keck team estimated that 3I/Atlas was releasing approximately 18 kilograms of material per second. That's about 40 pounds every second, mostly water vapour and carbon monoxide, blasting off the surface and into space. So case closed. Right. The acceleration is just outgassing doing its thing. Except here's the problem: when the JPL team modelled the expected acceleration from outgassing based on the observed gas production rate and the object's estimated mass, the numbers didn't match. The model predicted an acceleration of about 2.1 x 10⁷ meters per second squared, but the actual measured acceleration was 4.6 x 10⁷, more than twice as strong. Dr. Davide Farnocchia, a navigation engineer at JPL who led the analysis, explained it in a NASA technical briefing on November 15th. Either we're significantly underestimating the gas production, which is possible if there's outgassing we can't see on the night side of the object, or the efficiency of the rocket effect is higher than our models predict, or there's a third factor we're not accounting for. What could that third factor be? One possibility is asymmetric mass distribution. If 3I/Atlas isn't a solid chunk of ice and rock, but instead a loosely bound collection of fragments, what scientists call a rubble pile, then outgassing from internal voids could produce thrust without creating visible jets. Think of it like steam escaping from cracks deep inside the object, pushing on the structure from within. Another possibility is thermal lag. The surface of a rotating comet doesn't heat up and cool down instantly. There's a delay, usually a few hours, between when a spot on the surface faces the sun and when it reaches maximum temperature. That means the hottest, most active outgassing might happen slightly after the surface has rotated past the subsolar point. And if that timing is off by even a small amount, it changes the direction of the thrust and can create acceleration that looks anomalous. But here's the explanation that has some researchers genuinely excited, and it relates directly to that weird carbon monoxide chemistry we talked about earlier. Carbon monoxide ice sublimates at much lower temperatures than water ice. Water needs to warm up to about -100 degrees Fahrenheit before it starts vaporizing significantly. Carbon monoxide starts going at -330 degrees Fahrenheit. That means if 3I/Atlas has substantial carbon monoxide ice on or near its surface, it could be outgassing vigorously even in areas that never see direct sunlight, driven purely by the faint warmth of starlight and its own internal heat. Dr. Olivier Hainaut from the European Southern Observatory, speaking at the American Astronomical Society meeting on November 20th, said, "If this object is rich in supervolatiles like carbon monoxide and methane, it doesn't need the sun to activate it. It's essentially a comet that's always on, continuously venting material regardless of solar distance." That would explain both the early onset of activity we observed in August and the stronger than expected acceleration we're measuring now. Think about the implications of that. Most comets are dormant in the outer solar system and only wake up when they cross inside Mars's orbit. But an object from another star system, made of different ices, might behave completely differently. It might be active continuously, slowly losing mass over millions of years as it drifts through the galaxy. By the time we see it, we're catching a snapshot of an object in the middle of a slow-motion disintegration that's been happening for eons. And if that's true, then every interstellar object we detect might be a fraction of its original size. The version of 3I/Atlas that got ejected from its home system millions of years ago could have been 10 times larger, 100 times larger. We're seeing what's left after millions of years of erosion by cosmic rays and self-outgassing. Now you might be wondering, what if the acceleration is just outgassing, why is there still debate? Why can't scientists just agree on the explanation and move on? The answer is because the stakes are incredibly high. How we interpret the behavior of these objects determines how we model the population of interstellar visitors, which determines how many we think are out there, which determines the likelihood of detecting more, which determines whether we should invest in missions to rendezvous with them. And there's one more thing that complicates the picture. Something that showed up in the latest round of spectroscopic data and has researchers second-guessing everything they thought they understood about this object's composition. On November 18th, James Webb took another deep spectroscopic observation of 3I/Atlas, this time with longer exposure and broader wavelength coverage than the September run. The data came back 2 days later, and when the spectroscopy team at Goddard Space Flight Center processed it, they found a feature they absolutely were not expecting: a weak but definite absorption line at 3.47 microns. That wavelength corresponds to aromatic hydrocarbons, specifically polycyclic aromatic hydrocarbons, or PAHs for short. These are ring-shaped carbon molecules, some of the most complex organic compounds we know of in space. And here's why finding them on 3I/Atlas is such a big deal. PAHs don't just form anywhere. They require specific conditions, usually involving ultraviolet radiation breaking apart simpler carbon compounds and reassembling them into more complex structures. They're common in interstellar dust clouds, in the atmospheres of carbon-rich stars, and in the outer layers of protoplanetary disks where young planets are forming. But finding them on a comet, that's rare. Even in our solar system, we've detected PAHs on a handful of comets, most notably on 67P/Churyumov-Gerasimenko, when the Rosetta spacecraft sampled its coma directly in 2015, but those were trace amounts, parts per billion. The signal from 3I/Atlas suggests a concentration at least 5 times higher. Dr. Natalie Batala, an exoplanet researcher at UC Santa Cruz who's been collaborating on the Webb observations, posted a thread on Blue Sky on November 22nd that got massive attention. She wrote, "PAHs are essentially the soot of space. They form when organic chemistry gets hit with intense radiation and heat. Finding elevated levels on an interstellar comet suggests the disk it formed in was bathed in UV radiation, possibly from nearby massive stars. This thing might have condensed in a stellar nursery, surrounded by the kind of radiation environment that would sterilize any emerging life, but also drives the complex chemistry that could eventually lead to it. Let me break down why that matters. Our solar system formed in relative isolation, far from any giant stars that could flood the region with deadly radiation. That gentle environment allowed fragile organic molecules to survive and eventually seed the early Earth with the chemical building blocks for life. But most star systems don't form in isolation. They form in clusters, sometimes containing hundreds or thousands of young stars all packed into a region just a few light years across. And in those clusters, the biggest, hottest stars pump out ultraviolet radiation that can dominate the entire neighbourhood. If 3I/Atlas formed in that kind of environment, its chemistry would reflect it. The PAHs are a signature of radiation processing. a fingerprint of a violent birth. And that tells us something profound. Not all planetary systems start with the same chemical inventory. Some begin with pristine, radiation-shielded organic molecules. Others begin with molecules that have been cooked, broken apart and reassembled by starlight. And yet both types of systems might eventually produce planets, atmospheres, and maybe even life, just through different pathways. But wait, there's more in the spectrum. Buried in the data at 4.67 microns, the team found another absorption feature carbon dioxide ice. Solid CO2, frozen onto the surface. That's not surprising by itself. Lots of comets have carbon dioxide. But the ratio of carbon dioxide to water was off. Way off. In a typical solar system comet, CO2 makes up maybe 5 to 15% of the ice by volume. In 3I/Atlas, the spectral modelling suggests it's closer to 30%. Why does that matter? Because the ratio of these ices tells you the temperature and pressure conditions in the protoplanetary disk where the object formed. Water ice dominates when temperatures are just below freezing and there's plenty of oxygen available. Carbon dioxide becomes more abundant in colder regions, beyond what's called the CO2 snowline, where temperatures drop below minus 125 degrees Fahrenheit. The fact that 3I/Atlas is so enriched in CO2 suggests it formed very far from its parent star, possibly 30 or 40 astronomical units out, equivalent to the distance of Neptune or beyond in our solar system. Dr. Will Grundy, an astronomer at Lowell Observatory who specialises in ice chemistry, told Space. In an interview published November 25th. You can think of these interstellar objects as messengers carrying information encoded in ice. The mix of ices tells you the temperature, the isotopic ratios, which we're still working on measuring, will tell you about the nuclear processes in the parent star. The organic content tells you about radiation exposure. It's like reading a book written in frozen chemistry, and every page reveals something about a world we'll never visit. Now here's where things get even more interesting. The Webb team also measured the deuterium to hydrogen ratio in the water ice, looking at a specific absorption feature at 4.1 microns that's sensitive to deuterium, a heavy isotope of hydrogen. Deuterium forms in the early universe and gets incorporated into water molecules during the cold collapse of interstellar clouds. The ratio of deuterium to normal hydrogen in water is a tracer of where and how that water formed. In Earth's oceans, the deuterium to hydrogen ratio is about 156 parts per million. In comets from our solar system, it ranges from about 150 to 300 parts per million, depending on where in the solar system they originated. The preliminary measurement from 3-way/8-lace, approximately 420 parts per million, significantly higher than anything we've measured locally. That elevated ratio tells us the water on 3I/Atlas formed in a colder environment than the water in our solar system, possibly in the outer regions of a protoplanetary disk around a cooler star, or in the interstellar medium itself before being incorporated into the disk. It's direct evidence that the raw materials for planets vary across the galaxy, shaped by local conditions that we're only beginning to understand. Have you ever thought about the fact that the water in your body, the hydrogen and oxygen atoms in every cell, came from comets and asteroids that bombarded the early Earth? And those comets formed here, in this solar system, from this specific set of conditions. But if Earth had formed somewhere else, seeded by different comets with different chemistry, would life have emerged differently? Would you be made of slightly different stuff? These are the questions that 3I/Atlas is forcing us to ask. Not just what is this object, but what does it tell us about the diversity of planetary ingredients across the galaxy? Because if every star system produces slightly different comets with slightly different chemistry, then every planet that forms will inherit a unique chemical legacy. and that matters for understanding where life can emerge and what forms it might take. But all of this chemical analysis, all of these spectroscopic measurements, they're based on one big assumption that we're interpreting the shape of this object correctly. And as it turns out, that assumption might be wrong. Remember those light curve measurements we talked about? The brightness variations that suggested a 1.5 to 1 length to width ratio. Well, on November 27th, a team using the Very Large Telescope in Chile released new data that complicated that picture significantly. They'd been monitoring 3 I/Atlas in multiple wavelengths simultaneously, watching how its brightness changed, not just in visible light, but also in near-infrared and thermal infrared, and the patterns didn't match. In visible light, the object showed a clean periodic brightness variation with that 8.7-hour cycle we mentioned, but in thermal infrared, which measures heat rather than reflected sunlight, the brightness curve was different. It showed 2 peaks per rotation instead of 1. That's the signature of something that's not a simple elongated shape. It's the signature of what astronomers call a contact binary. 2 distinct lobes stuck together, rotating around their common centre of mass like a cosmic dumbbell. Dr. Colin Snodgrass, who led the VLT observation campaign, published the findings in the Astrophysical Journal Letters on December 1st with this quote in the abstract: "The thermal emission pattern is inconsistent with a monolithic rotating body and strongly favours a bilobed morphology. We may be observing a gentle collision frozen in time. 2 objects that merged at low velocity and have remained loosely bound ever since." Think about what that means. 3 I/Atlas might not be a single coherent object that formed through gradual accumulation of ice and dust. It might be 2 separate objects that collided sometime during its journey through the galaxy. Maybe it happened billions of years ago in its home system. Or maybe it happened relatively recently, a chance encounter in interstellar space where 2 ejected comets found each other in the darkness and stuck together at walking speed. Contact binaries are actually common in our solar system. Comet 67P, the one Rosetta visited, is a contact binary. So is the Kuiper Belt object Arakoth, which New Horizons flew past in 2019. They form when 2 objects in similar orbits drift together and merge gently, like docking spacecraft, but finding one in an interstellar visitor, that's new data. And it raises immediate questions about collision rates in interstellar space and whether these objects are constantly evolving, breaking apart and recombining as they drift through the galaxy. But here's where the shape mystery gets truly bizarre. On December 5th, just 3 days before 3 I/Atlas reaches its closest point to the Sun, amateur astronomer Sebastian Voltmer in Germany captured something extraordinary using a 14-inch telescope and lucky imaging technique, where you take thousands of short exposures and combine only the sharpest frames. His image, posted to the amateur astronomy community and later verified by professional astronomers, showed the nucleus of 3 Y/Atlas, not as a smooth blob, but with a distinct notch or indentation on one side. That notch could be a crater from an ancient impact. It could be a vent where outgassing has eroded the surface. Or, and this is the possibility that has some researchers genuinely excited, it could be evidence of active fragmentation. The object might be breaking apart right now, in real time, as we watch it. Comets do this. They're fragile, held together more by ice than by gravity. And when that ice sublimates rapidly, especially during close approach to the Sun, the structural integrity can fail catastrophically. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before slamming into Jupiter in 1994. Comet Linear fragmented into dozens of pieces in 2000. Just this past year, Comet 12P/Ponsbrook showed signs of outburst activity that could be precursors to splitting. If 3 I/Atlas is fragmenting, we might be watching the death of an interstellar traveller that survived millions of years in the cold of space. only to be torn apart by the warmth of our sun. The irony is almost poetic. It crossed light years of empty void, endured cosmic ray bombardment, probably survived close encounters with other stars, and it's going to come undone here. In a solar system, it was just passing through. Dr. Kwanzi Ye from the University of Maryland, who specializes in comet fragmentation, told Nature on December 6th, "If this object splits, it's both a tragedy and an opportunity. We lose the intact sample, but we gain the ability to see inside it, to study material that's been protected beneath the surface for millions of years. It's like a natural core sample delivered by the universe itself." And there's precedent for this kind of thing revealing hidden treasures. When Comet Ison broke apart during its close solar approach in 2013, spectroscopic observations of the debris cloud revealed chemical signatures that were completely absent in measurements of the intact nucleus. The fragmentation exposed fresh material that had never been processed by sunlight, giving scientists a glimpse of primordial ice unchanged since the comet's formation. So teams around the world are now on high alert, telescopes scheduled and ready, waiting to see what happens when 3I/Atlas makes its closest approach to the Sun. Will it hold together? Will it fragment into a debris stream? And if it does break apart, what secrets will spill out? But the shape isn't the only mystery surrounding this object's physical structure. There's also the question of what it's made of beneath the surface. Because while spectroscopy tells us about the chemistry of the gas and dust being released, it tells us almost nothing about the nucleus itself. The solid core hidden beneath the coma. Is it a dense rock covered in ice? Is it a loosely packed snowball? Is it a heterogeneous mix of materials, like a fruitcake from space? The only way to answer that question is to measure the object's mass, and the only way to measure mass is through gravity. If 3I/Atlas had a moon, we could watch how they orbit each other and calculate the mass directly, but it doesn't. So instead, astronomers have to use indirect methods, watching how the object's trajectory changes due to its own outgassing and working backward to estimate mass, based on how much force that outgassing produces. The current best estimate, published by the JPL team on December 7th, puts the mass at approximately 3 to 8 billion kilograms, depending on assumptions about the efficiency of outgassing thrust. That's somewhere between the mass of a large iceberg and a small mountain. But the uncertainty range is huge, almost a factor of 3, which means the density could be anywhere from 0.3 grams per cubic centimetre fluffier than styrofoam to 1. 2 grams per cubic centimetre, about the density of solid ice. And that uncertainty matters because density tells you about formation history. A fluffy, low-density object formed through gentle accumulation of ice grains in a quiet disk. A denser object either formed through more energetic collisions or has been compressed by its own gravity or by external impacts over time. The density is essentially a fossil record of the object's past written in its internal structure. So as 3I/Atlas approaches the Sun and its outgassing intensifies, scientists aren't just watching to see if it survives. They're watching to see how it responds to stress, because that response will finally tell us what this visitor is actually made of. December 3rd, 2024. Perihelion 3I/Atlas reaches its closest point to the Sun at precisely 11:23 Universal Time, passing just 112 million miles from our star. That's closer than Earth, roughly the distance of Venus at its nearest. And for a comet that's been living in the freezing void of interstellar space for millions of years, suddenly being this close to a star is like stepping from a walk-in freezer directly into a furnace. Within hours, the outgassing rate exploded. Ground-based observers reported that the coma had expanded from 3,000 miles across to nearly 12,000 miles, a fourfold increase in just 6 hours. The jets that had been producing 18 kilograms of material per second were now pumping out an estimated 95 kilograms per second. That's 200 pounds of ice converting to gas every single second, carrying with it dust, organic molecules, and whatever else was frozen into the surface. The Hubble team, who'd been monitoring continuously, captured a sequence of images showing the coma's evolution in real time. And in those images, you can see something remarkable, the formation of a tail. Not the faint, diffuse haze from before, but an actual cometary tail extending more than 50,000 miles behind the nucleus, pushed away from the sun by solar radiation pressure and the solar wind. That tail is made of two components, though they're hard to distinguish in visible light. There's a dust tail made of solid particles ranging from microscopic grains to pebble-sized chunks, all following slightly different trajectories based on their mass and the radiation pressure acting on them. And there's an ion tail made of electrically charged molecules, mostly carbon monoxide and water that have been ionized by ultraviolet light from the sun, then swept backward by the magnetic fields in the solar wind at speeds exceeding 400 miles per second. Dr. Matthew Knight from the US Naval Academy, who's been studying comets for 2 decades, posted an analysis on the Planetary Science Institute blog on December 4th. What we're seeing is a textbook comet at Perihelion, except the textbook was written for objects from our solar system. The tail morphology is familiar, but the brightness and colour are slightly off. The dust appears redder than typical solar system comet dust, possibly indicating a different mixture of silicates and organic compounds. It's like looking at a familiar painting, but the artist used different pigments. The reddish colour is significant because it tells us about the size distribution and composition of the dust grains. Smaller grains scatter blue light more efficiently, making the tail appear bluish. Larger grains and grains coated in organic compounds preferentially scatter red light. The fact that 3I/Atlas's tail is distinctly red suggests either larger average grain size or a higher concentration of complex organics coating the dust. Either way, it's another data point showing that material from other star systems doesn't necessarily match what we're used to seeing here. But here's what really caught everyone's attention during Perihelion: the nucleus survived. As of December 5th, 48 hours after closest approach, the object was still intact, still outgassing, still following a predictable trajectory. There was no catastrophic fragmentation, no sudden brightening that would indicate a breakup. The notch that Sebastian Voltmer photographed was still there, visible in follow-up images from larger telescopes, but it hadn't grown or spawned new fragments. That tells us something important about the structural strength of interstellar objects. Despite being battered by cosmic rays for millions of years, despite the thermal stress of passing through an alien solar system, this thing held together. It's not a fragile rubble pile on the verge of collapse. It has integrity, cohesion, possibly driven by internal ice acting as glue between rocky components. However, and this is crucial, surviving perihelion doesn't mean it's unscathed. The VLT team's thermal imaging on December 6 showed that the surface temperature had spiked to approximately minus 40 degrees Fahrenheit on the sunward side, a full 300-degree increase from its pre-perihelion temperature. That kind of thermal shock causes ice to sublimate explosively and can create stress fractures deep in the interior. The object might have survived the initial passage, but it could still be weakened, primed to break apart days or weeks later, when the accumulated damage finally exceeds its structural limits. And then there's the rotation. Remember that 8.7-hour spin period? It's changing. Measurements taken on December 7th showed the period had decreased to 8.3 hours, meaning the object is spinning faster. That's the result of outgassing acting like tiny rocket thrusters distributed unevenly across the surface, creating torque that changes the rotation rate. It's called the rocket effect, and it's been observed on many comets, but it's particularly pronounced on 3I/Atlas because the outgassing is so asymmetric. If the spin-up continues, if the rotation rate keeps increasing, there's a critical threshold where centrifugal forces overcome the object's gravity and structural strength, and it tears itself apart from the inside out. For an object the size and mass of 3I/Atlas, that critical rotation period is somewhere around 3 to 4 hours. We're still far from that limit, but every bit of outgassing, every asymmetric jet pushes it closer. Dr. Naomi Rowe Gurney from NASA Goddard, who's been modelling the rotational dynamics, said in a press briefing on December 8th, "We're essentially watching a slow-motion disintegration, not catastrophic, not explosive, but gradual. Every time this object passes close to a star, which is probably done dozens of times over millions of years, it loses mass, spins up a bit, gets a bit weaker. Eventually, maybe not this time, but someday, it will spin just a little too fast and it'll come apart. And when it does, it'll add dozens of smaller fragments to the population of interstellar debris drifting through the galaxy." Have you ever thought about the life cycle of these objects? They're born in the chaos of planetary formation, ejected violently into interstellar space. Then they spend millions of years drifting, slowly eroding, occasionally passing through other solar systems where they heat up, outgas, weaken, and eventually fragment into smaller and smaller pieces until there's nothing left but dust. It's a kind of cosmic erosion driven by starlight and time. But while 3I/Atlas is busy surviving its brush with the sun, scientists are racing to extract every bit of information they can before it fades from view, because the object is now on its way out, accelerating away from the sun on a trajectory that will take it back into interstellar space. And there's one question that's been lurking in the background this entire time. A question that all the spectroscopy and imaging and trajectory analysis has been building toward. Could this object, or objects like it, carry life between star systems? The idea is called Panspermia, and it's one of the oldest and most controversial hypotheses in astrobiology. The basic concept is simple. Life doesn't originate independently on every planet. Instead, it spreads through space, carried on comets, asteroids, and objects exactly like 3I/Atlas, seeding world after world with the chemical ingredients or even living organisms themselves. If true, it means life on Earth might not have started here. It might have arrived from somewhere else, delivered by an interstellar visitor billions of years ago. Now, before you dismiss this as science fiction, understand that the hypothesis has legitimate scientific foundations. We know for a fact that material can be exchanged between planets. Rocks blasted off Mars by asteroid impacts have landed on Earth. We have Martian meteorites sitting in museums right now. If rocks can travel between planets in the same solar system, why couldn't they travel between star systems? And if rocks can make the journey, why not the organic molecules frozen inside them? Why not, potentially, microbial life in a state of suspended animation, waiting for the warmth of a new sun to revive it? The detection of complex organics on 3I/Atlas, those polycyclic aromatic hydrocarbons and carbon-rich compounds, adds fuel to this idea. These molecules are precursors to life, the chemical building blocks that, under the right conditions, can assemble into amino acids, nucleotides, and eventually the machinery of living cells. Finding them on an object from another star system proves that these ingredients exist elsewhere and can survive the journey through interstellar space. Dr. Chandra Wickramasinghe, a proponent of panspermia theory who's been studying this question for over 40 years, told Astrobiology magazine In an interview published December 9th, every interstellar object is a potential arc, carrying organic chemistry from one star system to another. The galaxy is not a collection of isolated biospheres. It's a connected network where material, and possibly life itself, flows between the stars over timescales of millions and billions of years. But here's the challenge. Surviving interstellar space is brutally difficult. Cosmic rays, high-energy particles accelerated to near light speed by supernovae and other violent events, slam into anything exposed in open space, shredding molecular bonds and mutating DNA. A typical comet-sized object drifting through the galaxy receives a radiation dose that would be lethal to any known terrestrial organism thousands of times over during a million-year journey. However, and this is the intriguing part, the interior of a comet is shielded. Ice is an excellent radiation barrier. A layer just a few meters thick can block the majority of cosmic rays. So while the surface of 3I/Atelas is being sterilized continuously by radiation, the interior, the deep frozen core that's been protected since the object formed, could theoretically preserve organic molecules, or even dormant microorganisms for millions of years. Scientists modelled this exact scenario in a study published in Astrobiology in 2019, simulating the survival of extremophile bacteria buried in ice and exposed to interstellar radiation levels. The results showed that at depths greater than 3 meters, survival rates for spores and dormant cells remained above 50% even after 10 million years of exposure. Deeper than 10 meters, and survival rates approached 90%. The ice acts like a cosmic bunker, preserving whatever is inside it against the harsh environment of space. Now, does 3I/Atlas contain life? Almost certainly not. The probability is vanishingly small. But does it contain the organic molecules that could become life given the right environment? That's not just possible, it's confirmed. We've literally measured them in the spectra, those PAHs, those carbon dioxide and carbon monoxide ices, that deuterium-enriched water. It's all there, frozen into the matrix of this object, waiting. And here's the profound implication if 3I/Atelas formed in a protoplanetary disk around another star, incorporated organic molecules from that environment, and then got ejected into interstellar space where it spent millions of years wandering the galaxy before passing through our solar system. Then it's proof that organic chemistry is being redistributed across the galaxy continuously. Star systems are not closed loops. They exchange material. And that means the chemistry that led to life on Earth might include contributions from dozens, hundreds, maybe thousands of other stellar nurseries across the galaxy. Think about that for a second. The molecules in your DNA, the carbon and nitrogen and oxygen atoms that make up your cells, they were forged in stars that died billions of years ago. But some of those atoms might have taken a detour through another star system before ending up here. You might literally be made of stardust that visited alien worlds. Dr. Anna Maria Barea, a computational astrobiologist at the SETI Institute, explored this idea in a paper published in the International Journal of Astrobiology in November 2024. She wrote, "The discovery of organic-rich interstellar objects forces us to reconsider the boundary between stellar systems. If complex chemistry can be transported between stars, then the origin of life on any given planet is not a local event. It's a galactic event, influenced by material from across a vast region of space." But there's a darker side to this idea too. If interstellar objects can deliver the building blocks of life, they can also deliver extinction. A large enough object, impacting a planet at interstellar velocities, would hit with enough energy to sterilize the surface. The asteroid that killed the dinosaurs was moving at about 12 miles per second, 3I/Atlas is moving at over 20 miles per second. If something the size of this object hit Earth, it would release energy equivalent to millions of nuclear weapons, vaporizing everything at the impact site and throwing enough debris into the atmosphere to block out the sun for years. Fortunately, 3I/Atlas passed us at a safe distance, over 200 million miles away at its closest, but statistically, Earth gets hit by interstellar objects too. It's rare, maybe once every few 100 million years for something significant. But it happens, and when it does, it's a coin flip whether it brings creation or destruction. The NASA Planetary Defense Coordination Office has been tracking this question closely. In a report published in August 2024 before 3I/Atlas was even discovered, they estimated that Earth encounters an interstellar object larger than 100 meters in diameter, roughly once every 100 million years. Most pass harmlessly, some might impact. And if one does impact, we'll have very little warning because these objects approach from random directions at high speeds, giving us months at best to detect and respond. So the same objects that might have seeded Earth with the chemistry for life, that might be spreading organic molecules across the galaxy, are also potential harbingers of catastrophe. The universe doesn't do irony, but if it did, that would be a pretty good example. What we do know for certain is that 3I/Atlas has given us data that will take years to fully analyse. The spectroscopic measurements alone contain thousands of individual data points, each one a clue about conditions in another star system. And as more interstellar visitors are discovered, we'll start to see patterns, statistical distributions that tell us how common different types of chemistry are across the galaxy. Because 3I/Atlas is leaving now, fading back into the darkness, but it won't be the last. By mid-December, 3I/Atlas was already 140 million miles from the Sun and accelerating outward at a pace that would carry it beyond the orbit of Mars by New Year's Day. The coma had begun to fade, shrinking from its peak diameter of 12,000 miles down to about 6,000 miles as the outgassing slowed. The magnificent tail that stretched 50,000 miles behind the nucleus at Perihelion was now fragmenting, breaking into diffuse streamers that would eventually dissipate completely as the dust and gas dispersed into the solar wind. Hubble took its last scheduled observation on December 14th, a final deep exposure that required nearly 8 hours of integration time to detect the now faint object against the background stars. The image showed a ghostly smudge, barely distinguishable from noise, moving at a rate of about 2 arcseconds per hour across the sky. By the end of December, 3I/Atlas will have faded to magnitude 24 too dim for Hubble to track reliably. By March 2025, it will be beyond the reach of even the James Webb Space Telescope. And then it's gone. Lost to observation, continuing its journey through the galaxy on a trajectory that will carry it toward the constellation Gemini, though it won't reach the distance of the nearest stars in that direction for another 50,000 years. By the time it passes within a light year of another star, whatever star system that happens to be, Earth's continents will have shifted. Our civilization will have risen and fallen a dozen times over, and the Sun itself will have drifted to a completely different position in the galaxy. But the data remains. Hundreds of spectra, thousands of images, precise astrometric measurements spanning 113 days from discovery to final observation. And that data is now the most detailed record we have of an object from beyond our solar system. Scientists will be analysing it for decades, publishing papers, running simulations, testing theories about planet formation and interstellar chemistry and the distribution of organic molecules across the galaxy. Doctor, Matthew Knight, who coordinated much of the ground-based observation campaign, told reporters during a NASA press conference on December 16th, "We went into this hoping to answer questions about where this object came from and what it's made of. We got answers to some of those questions, but mostly, we got better questions. We now know that interstellar objects are chemically diverse, that they can survive millions of years in space, that they carry complex organics. What we don't know is how common they are, how representative 3I/Atelas is of the broader population, and what other surprises are waiting out there. How common are they? That's the billion-dollar question, literally. Because the answer determines whether we should invest in dedicated missions to intercept and study these visitors up close. Right now, we're limited to remote observations, watching from hundreds of millions of miles away with telescopes. But imagine if we could send a spacecraft to rendezvous with one of these objects, to land on its surface, to drill into the ice and analyze material that's been frozen since before our solar system existed. NASA's been studying this possibility seriously since Oumuamua's discovery. The technical challenges are enormous. These objects move fast, approaching the inner solar system at tens of kilometers per second. To match velocity and catch up with one requires a spacecraft with enormous delta-v capability, more than any propulsion system we currently have can provide, unless you launch years in advance and happen to know exactly where the object will be. But there's a solution, and it's called Project Comet Interceptor. It's a European Space Agency mission, currently scheduled for launch in 2029, that will park a spacecraft at the Sun-Earth L2 point about 1 million miles from Earth, and wait, just sit there, dormant, scanning the sky for new comets or interstellar objects. And when one is detected on approach, the spacecraft will wake up, calculate an intercept trajectory, and launch itself on a one-way mission to fly through the object's coma, taking measurements and photographs at close range before transmitting the data back to Earth. If an interstellar object passes through during Comet Interceptor's operational lifetime, which could be anywhere from 5 to 10 years depending on fuel reserves, we'll get our first close-up look at one of these visitors. We'll see surface features, measure composition directly, maybe even collect samples of the coma gas and dust. It would be transformative for the field, Dr. Geraint Jones, the project scientist for Comet Interceptor, said during a European Planetary Science Congress presentation in September 2024, "We designed this mission specifically with the possibility of interstellar targets in mind. The spacecraft is fast, responsive, and carries instruments optimized for rapid flyby scenarios. If something like 3I/Atelas comes through while we're operational, we won't just watch it from Earth. We'll go meet it." And beyond Comet Interceptor, there are even more ambitious proposals on the drawing board. Project Lyra, a study funded by the Initiative for Interstellar Studies, explored the feasibility of launching a fast response mission to catch up with Oumuamua or future interstellar objects using solar sails and gravity assists. Their conclusion is possible, but barely, and only if we commit to building the spacecraft in advance and keeping it ready to launch on short notice. The technology exists. What's missing is the political will and funding to make it happen. But every new interstellar object we detect builds the case. Oumuamua proved these things exist. 2I/Borisov showed they're not all identical. 3I/Atelas demonstrated they carry complex chemistry and can survive close solar approaches. What will the fourth one show us? The fifth, the 10th, because they're coming? The statistical models, refined with each new detection, now estimate that we should be able to detect 2 to 3 interstellar objects per year with current survey capabilities. And as new telescopes come online, that number will increase. The Vera C. Rubin Observatory in Chile, scheduled to begin operations in 2025, will scan the entire visible sky every few nights, detecting objects far fainter than anything current surveys can see. It will revolutionize the field. Dr. Mario Uric, who leads the Rubin Observatory's data management team, posted on X on December 10th. When Rubin starts operating, we expect to detect dozens of interstellar objects per year. Maybe more. It's going to go from a trickle to a flood. We'll finally be able to do statistics on these populations, to categorize them, to understand what's typical and what's weird. 3i/Atlas won't be a curiosity anymore. It'll be a data point in a much larger data set. And that's when the real science begins. Because 3 objects don't make a pattern, 30 objects do. 300 objects let you draw conclusions about how planetary systems work across the galaxy. Do red dwarf systems eject more material than sun-like systems? Do heavy element-rich stars produce different chemistry than metal-poor stars? Are organic molecules common on all interstellar objects? Or was 3i/Atlas an outlier? These are questions we can't answer yet, but we will. Maybe not this year. Maybe not in 5 years, but within your lifetime. We'll have a catalogue of interstellar visitors detailed enough to rewrite planetary science textbooks. So where does that leave us right now? In December 2024, watching 3i/Atlas fade into the distance. What have we actually learned from these 4 months of intense observation?